Hello friends, I am Zeki. Today, my topic is Chapter 14, the processor structure and function. In this presentation, I will talk about how a processor is organized internally and how it actually executes instructions. A modern processor repeatedly performs five fundamental operations. First, it fetches the next instruction from memory. Second, it interrupts or decodes that instruction to understand what needs to be done. And then it fetches the required data operands either from registers or from memory. And then it processes the data using the arithmetic logic unit or other functional units. Finally, it writes the result back to a register or to memory. No matter how complex a program is, it's built from these same basic steps. The processor cannot work directly with main memory all the time because memory access is relatively slow. Instead, it needs temporary, very fast storage inside the CPU. It must remember where the last instruction came from so it can find the next one, and it must hold intermediate results while a current instruction is being executed. This is why we use registers and internal buffers. These small but extremely fast storage locations are critical for performance and for correct program execution. This slide shows the CPU connected to the rest of the system using the system bus. The CPU does not access to memory or I/O devices directly. Instead, it sends addresses, data, and control signals over the bus. The address bus tells which memory location or device is being accessed. The data bus carries the actual information being read or written. The control bus carries signals such as read, write, and interrupt. Together, these buses allow the processor, memory, and I/O devices to communicate as a complete system. Inside the CPU itself, we can identify several key components. There is an arithmetic logic unit, which performs operations like addition, subtraction, and logical comparisons. There is the control unit, which coordinates when each part of processor should be active. There are also internal buses and multiplexers that connect the registers and arithmetic logic unit and other units. These internal connections form data paths that determine how information flow inside the CPU. Understanding these structures help us how instructions are executed step by step. Registers are fastest storage elements in the system and they are located inside the processor. We divide into the two broad categories. User visible registers are accessible to programmers and compilers, and they are used to hold data, addresses, and sometimes condition codes. The control and status registers, on the other hand, they are mainly used by the CPU hardware and the operating system. They keep track of the current instruction and the next instruction and flags that describe the current state of the processor. User visible registers are designed to speed up the program execution by reducing the numbers of memory accesses. General purpose registers can be used for almost any operation, such as holding intermediate results or loop counters. Data registers may be specialized for arithmetic or logical operations. Address registers are used to hold memory addresses for instruction and data. Finally, condition code registers store bits that indicate information about the result of the last arithmetic or logic operation, such as 0, negative, or carry. In many architectures, general purpose registers are the main work area for computations. Some designs still include an accumulator register that is heavily used for arithmetic. Others include segment pointers and index registers, which help with more complex addressing modes such as arrays and structures. The stack pointer is a special register that marks the top of the stack, which is used for procedure calls, local variables, and return addresses. Together, these registers make data access and manipulation more efficient than always going to main memory. The control and status registers are not usually manipulated directly by application programs, but they are essential for correct operation of the processor. The program counter holds the address, and the instruction registers contain the instructions currently being executed. And the other one is memory address register and memory buffer register. They too act as a bridge between the CPU and memory during read and write operations. And these registers allow the control unit to manage the flow of instructions and data through the system. Let's talk about program status word. It's a special register or collection of registers that store important status information. It includes condition flags such as sign, zero, carry, or overflow that reflect the result of arithmetic or logical operations. It may also include the control bits such as the interrupt enable or disable flag and a supervisor note that indicates whether the processor is in user mode or privilege mode. The operating system relies on the PSW to manage protection, error handling, and the response to interrupts and exceptions. And this slide shows a concrete example of how registers might be organized in a real processor. You can see the split between general purpose registers, special purpose registers like the computer counter, and the status registers. Different architectures may arrange these registers differently or have different numbers of registers. And however, the same basic idea appears again and again. A small set of the very fast storage locations at the heart of the CPU, each with a specific role in controlling execution and holding the data. The instruction cycle is the fundamental loop that a processor follows while it's running a program. In simple terms, it is the time required to fetch a single instruction from memory, decode it, and finally execute it. Even though modern processors may overlap many instruction cycles through pipelining, conceptually, each instruction still goes through these steps. Understanding the instruction cycle helps us understand how complex programs are reduced to a series of very simple machine operations. The instruction cycle is divided into several subcycles. First, in the fetch cycle, the CPU reads the next instruction from memory into the instruction register. Second, there may be an indirect cycle, where the CPU performs additional memory access to obtain the effective addresses of an operand. Third, in the execute cycle, the CPU carries out the specified operations, such as an arithmetic calculation or a data movement. Finally, an interrupt cycle may occur to handle and pending interrupts before the next instruction is fetched. These subcycles give a modern detailed view of what is happening inside the CPU. And this diagram shows how control repeatedly moves through the different subcycles of the instruction cycle. Normally, execution flows from the fetch to execute backend to fetch again. If an instruction uses indirect addressing, an indirect cycle is inserted before execution. If an interrupt signal is detected, an interrupt cycle is inserted so that the processor can save its state and service the interrupt. And after that, the control returns to the fetch cycle and the normal sequence continues. This cyclic behavior is at the core of the CPU operation. Here we see the detailed data flow for the fetch step. The program counters places the address of the next instruction into the memory address register. The control unit then issues a read command to memory. The instruction at the address is loaded into the memory buffer register, then transferred into the instruction register. Meanwhile, the program counter is incremented to point to the following instruction. This process ensures a steady stream of instructions to be executed. The indirect cycle, the CPU first obtains the actual addresses of the operand because the instruction itself holds only an address of a memory location that contains that operand address. The processor uses the address from the instruction to access memory again. That memory location contains the effective address of the operand. Once the address has been loaded into the appropriate register, the CPU can proceed with an execute cycle as well. This extra level of indirection allows more flexible addressing but requires more memory accesses, of course. During the execute phase, the exact data flow depends on the instruction being processed. For an arithmetic instruction, the CPU will move the operands from registers into the arithmetic logic unit, perform the arithmetic operation, and then write the result back to a register or to the memory. For a load or store instruction, the CPU will either read data from memory into a register or write data from a register into memory. For I/O instructions, data may be transferred between the CPU and an I/O module. In each case, the control unit activates that required data, paths, and functional units. When an interrupt occurs, the CPU must temporarily stop what it's doing and service the interrupt. It first completes the current instruction so that the program state is consistent. Then it saves key information such as the current program counter value and the status flag, typically on a stack or in dedicated registers. And next, the CPU loads the addresses of the appropriate interrupt service routine from an interrupt vector table. Once the service routine finishes, the save state is restored on and execution resumes exactly where it paused. And this mechanism allows the processor to respond quickly to eternal events without losing its place in the program. Let's pass to the instruction pipelining. It's basically a technique used to improve the throughput to a processor. Instead of waiting for one instruction to complete all stages before starting the next one, the CPU overlaps different stages of multiple instructions. For example, while one instruction is being executed, the next one can be fetched, and the following one can be decoded. This is similar to an assembly line in a factory, where multiple products are in different stages of production at the same time. In here, the goal is to keep all parts of the processor busy and reduce idle time. And we see the two-stage instruction pipeline. A simple form of pipelining splits instruction processing into just two stages, just fetch and execute. The first stage fetches an instruction and stores it in a buffer. The second stage executes the instruction that data fetched earlier. And in this slide, the instruction pipeline into 6 more detailed stages. Fetch instruction, decode instruction, calculate operands, fetch operands, execute instruction, and write operand. Each stage performs a small part of a total work. Successive instructions are staggered through these stages so that, ideally, one instruction completes each clock cycle. This fine-grained division makes it easier to design high-frequency pipelines, but also introduces new challenges such as hazards and the need for careful control unit. Now we see the timing diagram for instruction pipeline operations. This diagram shows how instructions overlap in the pipeline. Each row represents an instruction and each column represents a clock cycle. As we move down the rows and across the columns, we see the different instructions occupying different stages at the same time. The key idea is that once the pipeline is full, a new instruction can complete every clock cycle, of course in theory. However, as we will see in the hazards, such as resource conflicts, data dependencies, and branches can interrupt this ideal flow as well. Now we see the 6-stage CPU instruction pipeline. This type of pipelines provide more opportunities for parallelism, but also requires more complex control. This alternative pipeline depiction of the pipeline emphasizes the flow of instructions through the stages rather than the timing view. Each instructions move from one stage to the next one each clock cycle, provided there are no hazards or stalls. And let's talk about RISC pipelines. Many RISC architectures use a standard 5-stage pipeline: instruction fetch, instruction decode, and instruction fetch, execute, memory access, and register write back. RISC instructions are usually simple and fixed length, which makes them easy to fetch and decode. Let's talk about pipeline hazards. Unfortunately, pipelining does not always work perfectly. A pipeline hazard occurs when the next instruction cannot start its execution in the next clock cycle. In other words, the smooth flow of instructions is interrupted. This can force the pipeline or part of it to stall, creating what is something called a pipeline bubble. A resource hazard, also called a structural hazard, happens when two or more instructions in the pipeline need the same hardware resources at the same time. For example, if instruction fetch and data access both need to use main memory and the memory has only one port, they cannot proceed in parallel. In 5-stage pipeline, each stage ideally takes one clock cycle and we would like to start a new instruction every cycle. But with a single memory port, either the fetch stage or the memory stage must wait. This creates a stall and reduces the effective throughput. A data hazard arises when two instructions that access the same data location are close together in the pipeline. If the first instruction writes a value that the second instruction needs to read, then the second instruction might read the old value if it's progressed too quickly. In a strictly sequential, non-pipelined execution, this problem doesn't appear because the first instruction always completes before the second starts. But in a pipeline, multiple instructions are in the progress at the same time, so we should take special care to preserve the correct data dependencies. Now we see the data hazard diagram. The data hazard diagram visualizes how the timing of the reads and the writes to a particular register overlap across the multiple instructions. It shows at which clock cycle an instruction provides a value and when another instruction needs that value. By examining this diagram, hardware designers can identify where stalls or forwarding paths are required. Let's talk about control hazard. It's also known the branch hazard, occurs when the pipeline makes the wrong guess about the flow of control. For example, after a conditional branch instruction, the CPU may not know immediately whether the branch will be taken or not. If it guesses wrong and fetches instructions from the wrong path, those instructions should later be discarded. This wastes cycle and can significantly reduce the benefits of pipelining. Now we will talk about branches. Branches are instructions that change the normal sequential flow of executions. They allow the program to jump at different instruction addresses, enabling loops, if then else statements, and function calls. A branch instruction typically has an operand that specifies the target address. When the branch is taken, the program counter is updated to this target, and the next instruction is fetched from there. Without branches, the program would only run in a straight line with no decisions or repetition, which is obviously not enough for real applications. We can distinguish between unconditional and conditional branches. An unconditional branch always transfers control to the target addresses regardless of any condition. A conditional branch, on the other hand, checks a condition often based on the condition codes in the program status word. In a pipeline processor, branches disrupt the steadily flow of instructions into the pipeline. If we do nothing special, we must wait until the branch is resolved before fetching the next instruction, which can lead to many idle cycles. To maintain a high instruction throughput, designers use various techniques to reduce or hide the penalty of branches. In this slide, I listed 5 main approaches to dealing with conditional branches in a pipeline. These are multiple instruction strips, delayed branching, prefetching the branch target, loop buffers, and branch predictions. Multiple streams means that the pipeline fetches instructions along both possible paths and branch, trying to stay ahead regardless of the outcome. However, this can lead to resource contention and is difficult to scale. Delayed branching is an architectural technique where the effect of the branch is delayed by one or more instructions, and the compiler fills these delays slots with useful work. Prefetching the branch target involves fetching the target instruction in advance so that if the branch is taken, the target is already in the pipeline. Loop buffer is a small, high-speed memory that stores the most recently fetched instructions. This is particularly effective for short loops, where the same instruction execute repeatedly. And lastly, branch prediction techniques attempt to guess whether a branch will be taken or not. Static prediction uses simple rules, while dynamic prediction monitors the actual runtime behavior of the branches. This flowchart shows the decision-making process of a branch prediction mechanism. When the CPU encounters a branch, it consults its prediction logic to decide whether to fetch from the branch target or from the next sequential address. Later, when the branch condition is resolved, the processor compares the actual outcome with the prediction. This state diagram represents more detailed model of branch prediction, such as 2-bit saturating counter. Each branch has an associated state that reflects how likely it's to be taken, based on the recent history. Every time the branch is encountered, the predictor consults this state to make a prediction. When the branch is actually resolved, the predictor transitions to a new state depending on whether the prediction was correct or not. The Intel 80-486 was an important step in the evolution of x86 processors, introducing a more advanced pipeline. In the fetch stage, instructions are fetched from the cache or external memory into the one of two 16-byte prefetch buffers. The CPU works to keep these buffers full so that the decode and execute stages rarely have to wait. Decode stage 1 examines the opcode and addressing more information, often using only the first few bytes of the instruction. It prepares control signals and may direct the second decode stage to fetch the remaining bytes. In decode stage 2, the processor expands the partially decoded opcode into a full set of control signals and computers and complex effective addresses such as base plus index plus displacement. The execution stage then performs the arithmetic logic unit operations, accesses the cache when needed, and updates registers. And finally, the write-back stage, the results are written to the appropriate registers and possibly to cache or memory through the write buffers. This slide shows concrete examples of the instruction sequences flowing throughout 80-486 pipeline. Now we will talk about x86 processors. This processor family is based on the CISC architecture with a large and complex instruction set. It supports many addressing modes and instruction formats, and it's evolved over decades, maintaining backward compatibility. Internally, x86 processors have a deep register hierarchy and advanced interrupt handling mechanisms. The Pentium 4 architecture includes a wide variety of registers. In addition to these general purpose integer registers, there are floating point registers, SIMD registers for multimedia and vector operations, and various control and status registers. The E-flag register in x86 holds many of the condition codes and control bits that influence how instructions behave. Condition flags such as 0, sign, carry, and overflow are set or cleared by arithmetic and logical operations and are used for conditional branches and other decisions. Control registers in x86 such as CR0 through ZR4 are used primarily by the operating system. They manage crucial system functions like paging, memory protection, and the enabling of certain processor modes. MMX technology introduced a set of 64-bit registers designed for integer-based multimedia operations such as image and audio processing. And interestingly, MMX registers are not completely separate. They are aliased onto existing floating point register set. This means that the lower 64 bits of the floating point registers are reused for the MMX operations. The advantage is that no additional physical registers are needed, but the disadvantage is MMX and floating point instructions cannot be freely mixed without managing this overlap. In the Pentium architecture, interrupts and exceptions are handled using an interrupt vector table. Each type of interrupt is assigned a number that serves as an index into this table, which contains the address and corresponding service routines. ARM is a RISC architecture that emphasizes simplicity and efficiency. Its instructions are typically of fixed length, which simplifies fetching and decoding. ARM supports multiple processor modes and uses banked registers to speed up the mode switching. In this slide, I gave more detail about internal organization of ARM processor. Data and instructions are transferred between the processor and memory using a data bus. Instruction pass through a decoder, then into a pipeline where control signals are generated. The register file contains 32-bit registers that hold operands and results. ARM supports different data sizes such as bytes and half words, which are sign extended as needed. ARM supports a user mode and several privilege modes that are used by the operating system for different types of exceptions and system tasks. These are 6 privileged modes, including supervisor, abort, undefined, IRQ, and FIQ modes. Each mode can have its own banked registers for critical values like stack pointer and link register. An ARM register organizations includes 37 physical, 32-bit registers of the 31 are general purposes. Some registers have special roles such as program counter and various status registers. And the registers are arranged in partially overlapping banks, meaning that different processor modes can see different subsets of physical registers. And finally, ARM supports multiple types of exceptions, including reset, undefined instructions, software interrupts, and both normal and fast hardware interrupts. When an exception occurs, the processor completes the current instructions and then switches into the appropriate exception modes. It copies the current program status into a saved program status register for the mode and stores the address of the next instruction in the most linked register. The program counter is loaded with the address of the exception vector, which points to the handler. When the handler finishes, it restores and saves status and returns by moving the saved link register back into the program counter, thus resuming normal execution. And that's the end of my presentation, friends. Thank you for your attention. Have a good day.